Okay, we are continuing on here, chapter 17. We've been talking obviously about electrochemistry, and we did some galvanic cells obviously last time. We related it to sort of our equilibrium constant. We also talked about the Nernst equation. We have our E of a cell is equal to RT/F natural log of K. We also have our E is equal to our E naught minus RT natural log NF natural log of Q, which obviously this is the Nernst equation, which we could use when we're under non-standard conditions. So that's basically what this sort of E is. Remember that basically non-standard conditions are something to do with maybe concentrations or pressures. They're not 1 atmosphere or 1 molar. That's very common, and that will give us our E of the cell afterwards. And again, as we talked about, to get back to this guy at equilibrium, E is equal to 0 and Q would equal K. So again, that's how we kind of get back to that guy's equation. We also talked about, I think, at the end there, batteries and corrosion, and what you need to know, as we talked about, similarities between traditional batteries and obviously traditional galvanic cells, and differences. We also need to know what corrosion is and a couple ways to prevent it. And we finished up talking about electrolysis, kind of where we're at actually. And electrolysis is really the process where we use sort of an external electrical energy basically to make a non-spontaneous process occur. So for example, if we had some sodium chloride and we really wanted to sort of take the sodium chloride back into its elements, we would be doing some process like this. We could run an electrical current through it and it will do it. Remember though, in an electrolysis cell, it's sort of like the backwards reaction or the reverse reaction of maybe making something like sodium chloride. So as we talked about, when we make something like sodium chloride, in terms of oxidation states, these guys are 0, that's +1 and -1. So it's actually the sodium here that is being oxidized and is your anode. And it is the chlorine here that's being reduced and is your cathode. But when we do travel sort of in the opposite direction there and do the electrolysis cell, this guy is +1, this one is -1. This is 0 and 0. And in this particular case, it is actually the sodium here that is becoming more negative. And it's actually the sodium ion here that is getting reduced, which would be our cathode. And it is the chloride ion that is being oxidized, which would be our anode in this case. So running the electrolysis cell, we really have something like this. Plus a couple of electrons going to our 2 sodiums, and we have our 2 chlorides releasing our 2 electrons here. So again, that's our anode reaction and our cathode reaction, which is essentially opposite of, again, kind of putting it together. So sometimes people will get the half reaction sort of incorrect when they're going the opposite way in terms of electrolysis. Any questions on that there? Okay, so we also could do something like the electrolysis of water. So under normal conditions, right, water will not break apart into its sort of elements, but you can you can then apply an electrical current to water, and you can generate hydrogen gas and oxygen gas here by doing that. And in this case, our anode reaction is water making our O2, and that's basically the oxygen going from -2 to 0 in this particular case, so becoming more positive and going through oxidation. And here's the hydrogen going from +1 to 0 in this case, and it's becoming reduced in this case, and that is your cathode reaction. Usually when you do something like electrolysis of water, you got something like some type of acid that's usually added to the water. And a lot of times in book type problems, they may not just straight up say you're doing the electrolysis of water. They may just say something like dilute sulfuric acid is used in an electrolysis cell. And basically what that is basically the electrolysis of water. So sometimes with water, they don't kind of come straight out and say you're doing the electrolysis of water. So if you do see something like that, like you're using dilute sulfuric acid in an electrolysis cell, these are really going to be your half reactions that are going to occur. And it's really that electrolysis of water. And that's what we see here. You could actually do this with like a 9-volt battery, some electrodes, and some acidic water. And we have our hydrogen being filled in here, and this our empty spot in the flask. And we also have our oxygen being filled in that empty spot in the flask. And if we look at our amount of gas there between the two, there's more hydrogen than oxygen. That's because water is H2O, right? You get 2 hydrogens for every oxygen, so you get twice as much hydrogen gas that comes out. And that reddish area that I just colored in is where the gas obviously would be in this particular case. Now, sometimes when we deal with electrolysis, a lot of times one of the things that we're interested in is, how much of the element we're going to make. So in a lot of cases, there's a couple of ways we kind of end some of these problems. Our calculations with these type of problems is we look for maybe how many grams we would produce. So a lot of times that involves the molar mass and moles. But in a situation like this, perhaps when we're dealing with gases, sometimes we do look for something like how much volume of the gas that we produce. So sometimes in electrolysis problems, our friend, the ideal gas law comes back into play, and we use the ideal gas law to ask and solve for a lot of times how much volume of gas was sort of collected when you do this. A reminder that when you use the ideal gas law, everybody's got to be in the correct units. It's got to be atmospheres for pressure, has to be liters for volume, and should be moles. T here should be Kelvin. And the R in this case is the 0.08206 version of the gas constant. R if you used a rounded version, that guy as well. So sometimes in electrolysis problems, you do have to kind of harken back there to the ideal gas law, especially when you're dealing with gases. Again, that's a very common sort of outcome to it. Any questions on that there? So let's talk a little bit about the calculations that we typically do in an electrolysis cell. Not too bad in terms of how we go about doing it, but let's talk a little bit about it. So usually in a sort of electrolysis sort of problem, they will give you the amperage at which the cell is run for, and basically how long you run the cell for. They'll say, hey, you ran the cell at 4 amps for like 3 hours or something like that. And a lot of times you're interested in, again, how much of those sort of elements you're going to sort of collect as a result of doing that. So an important relationship is a coulomb is an amperage per second. So coulomb is equal to an amperage times a second, which means an amperage is the same as a coulomb per second. Is sort of a conversion factor, is really good. You want to get the charge in coulombs, and you get that basically by taking your amperage, which is coulombs per second, and you times it by the time. That's also in seconds, so that they cancel out basically, and you will end up with the coulomb of charge. That also usually requires some type of conversion, because most of the time they'll tell you you ran it for 2.5 hours. You need to convert it eventually to seconds so the units cancel out correctly. Once you have the charge in coulombs, we want to really figure out the number of moles of electrons there are. And that is where our friend Faraday is going to come into play. We're going to basically use Faraday's constant here, which is 96,500 coulombs, which is 96,484, if you want to use the real number, is equal to 1 mole of electrons. And we're going to use that really as a conversion factor to go from coulombs to moles of electrons. At this point, we're going to know pretty much how many moles of electrons we produce from the cell. And this is where the balanced half reactions for what's going on in your electrolysis cell is really important, because if you look at your reactions, depending on which one it is, there will be some electrons on one side of the half reaction. And you're basically just going to do stoichiometry, however many moles of electrons there are to how many moles of like the metal you're interested in, or maybe it's the gas you're interested in, whatever it may be. But you're basically just going to do kind of a stoichiometry sort of calculation, moles of electron to moles of what you're interested in. At that point, you're pretty much at the end of the calculation. It just depends on sort of what they're looking for in terms of the final answer. So you will at some point here, after you do that, have moles of what you're looking for. And really, if you want grams, that's going to be a molar mass type of calculation that you need to do at the end. If you want volume, probably it's a gas, and probably PV equals nRT is probably the approach that you need to do. So that's sort of the common sort of pathway in these electrolysis problems. Again, a lot of times they'll give you the amperage and the seconds or the time, convert it to seconds, get to the coulombs, use Faraday's constant to get the moles of electrons, balance half reaction, gets you to moles of what you're interested in, and then obviously depending on what you're looking for, either the molar mass or the PV equals nRT if it's some type of gas. Any questions on that one? All right, so why don't we try one here to see. We're going to come back to this one. We'll try this last one I think you have first. All right, so we run this particular electrolysis cell of calcium chloride, and it runs at a current of 0.452 amperage for 1.5 hours. How much calcium will we produce? So we're looking for how many grams of calcium in the cell. Calcium from the periodic table, 40.08 grams per mole. So why don't you give it a try, see where you get to, and then we'll talk about it here. Okay, let's take a look. So again, in this case, we are given the amperage. We're also given the time that we're going to run this cell, and we really want to know basically how much calcium we're going to produce. Remember, in this case, we're actually starting with calcium chloride, and we're basically going to try to get to calcium, no charge, and chlorine here in this particular case. And in terms of what's going on, this is +2, that is -1, that is 0, and this is 0. So once again here, it is the calcium that's going from +2 to 0. It's actually becoming more negative and is being reduced, which is why it is our cathode in this case. And it is the chloride going from -1 to 0 here, becoming more positive, and that is going to be our anode. So again, we're running this backwards. Obviously, that's opposite of what it would be if we were putting it together. And that's why we do see our half reaction written in that direction. Now that we have that, 0.452 amperage is the same as 0.452 coulombs per second. And sometimes it's helpful to kind of convert it into those units so you can kind of see the units that you want to use in the calculation. That also tells us that we need to do a little conversion here, right, of our hours to seconds. So 1.5 hours, I think there's like 3,600 seconds in an hour. I hope not 60, right? Which I did the other day for a while there before I realized no, it's more 60. So now we have seconds and we have really our amperage. We're just going to basically multiply those together, and we're going to take our 5,400 seconds times our amperage here. That's in our coulombs per second. That's going to allow our seconds to cancel, and that will get us 2440.8 coulombs. This is the point where we're going to now use Faraday's constant really to convert that into moles of electrons. So we're going to divide by Faraday's constant, which is 96,500 coulombs per mole of electron. So again, that's going to allow us to get into the moles of electron, which will then allow us to use our half reactions here in a second. We'll call it 0.0253 moles of electrons. Any questions so far here? Now that we have the moles of electrons, we're interested in calcium. So we want to go to the balance half reaction for calcium. And we want basically to do a stoichiometry sort of move. And we can see that for every 2 moles of electrons, we get 1 mole of calcium. And that's what's going to allow us to go from electrons to calcium. So if we do that, 0.0253 moles of electrons, using the half reaction there, 2 moles of electron, 1 mole of the calcium. Right, so that's going to cancel. And if I divide that by 2, we're going to go with 0.0126 moles of calcium. I used the whole number. I didn't use the rounded number, so you might got 0.0127 if you rounded it at the end there. At this point, though, we don't really want moles, but we do want grams. So in this case, we are going to use the molar mass here to convert those moles into grams. And that's going to be from the periodic table, 4008 grams per mole of calcium. And that's going to tell us that if we ran this cell for that many hours, we will produce a whopping 0.507 grams of calcium should come out of the area. Any questions on that there? Now, clearly, we could have, if we were interested in chlorine as well, done a similar calculation for chlorine in this case. It really would be the same calculation up to here. And in this case, we would go to the chlorine half reaction. Actually, we would have the same relationship there. And if we did that, it would be 0.0253 moles of chlorine, sorry, electron. And there are 2 moles of electron for 1 mole of Cl2, which would give us 0.0126 moles of Cl2. And at that point, you know, if we wanted grams, we could obviously use the molar mass like we did for the previous one. If we had maybe a pressure and some temperature given to us as well, we could have maybe, you know, figure out a volume or something like that. So there's some variations as to where you could end with that. Any question on that there? Okay, then let's go back to that one we skipped and let's try that one there. We're going to do basically the electrolysis of water. So we're going to run this cell through sulfuric acid. So as I mentioned earlier, this is really talking about water. And the key that we know this water, even though it doesn't really mention water, is sulfuric acid. So that's how we know. Again, we're kind of doing the electrolysis of water here. And we're going to run this cell at 1.26 amperage for 7.44 hours. And we want to know what is the amount of volume of each gas. So the hydrogen gas and oxygen gas at STP. STP is standard temperature and pressure. Temperature is 273, right? Pressure is 1 atmosphere. Yeah. So why don't you give it a go? The reactions are right there. So you don't have to write them, but they're right there is the half reactions for water. So why don't we just copy that stuff over to this slide, maybe. We're going to run it at 1.26 amperage for, I believe it was 744. STP. Volume of hydrogen gas and oxygen gas. All right, so see what you come up with. You get 2 answers there, volumes of each of those gases. And again, temperature means 273 and pressure is 1 atmosphere. Okay, let's take a look, see how you're doing. So in this case, we're looking for the volume of 2 different gases here. And again, as we saw in the last problem there, it says the electrolysis in using sulfuric acid. So we do know it's water. So we want to make sure we use the right half reactions here. We do need to do a little bit of conversion here. We're going to need to get our time there into seconds. So we'll do that. And that's going to be, again, 3,600 seconds per hour. And that will get us 7.44 times 3,600 about 26,784 seconds. I'm going to then multiply that by the amperage, which is basically 1.26 coulombs per second, as this is a coulomb per second, basically. Same thing, the A is the same. All right, so that's going to get rid of our seconds. And if we do that, we will end up with 7.84 coulombs. At this point, that's our electrical charge we're going to generate. We're going to use Faraday's constant to convert that into moles of electron. Then we'll be in some good shape, hopefully. Coulombs. We're going to divide by our 96,500 coulombs per second, moles of electrons. There we go. And if we do that, 96.5, gonna get us about we'll call it 350 moles of electron. Any questions so far? Now, this is where our sort of half reactions are going to come into play. If we look up here, we can see that for our anode side, it is 4 electrons for every 1 mole of oxygen gas. So to get the moles of oxygen gas, we will take our moles of electrons. We'll use the half reaction as a conversion factor. 4 moles of electrons, 1 mole of O2. And that gets us 0.35 divided by 4. Looks like 0.0875 moles of O2. We also obviously want to do it for our hydrogen gas as well. So if we go to our guy here is our electrons, here is our hydrogen, but we also have a 4 on the outside, which needs to be distributed in there. And that basically would give us 4 moles of electrons is equal to 2 moles of H2. So you could use it like that if you like. That's the same as obviously a 2-to-1 relationship. You could use it like that if you like as well. So we'll use that there to get to our moles of hydrogen. 0.35 moles of electrons. I'm just going to use the 4-to-2 relationship there. So 4 moles of electrons, 2 moles of H2. And that's going to get us basically the same as obviously a 1-to-1/2 relationship there. We got 0.350 times 2 divided by 4. Going to give us 0.175 moles of hydrogen. Any questions up to there? Yeah. You could, it comes the same. You could use 1 mole of hydrogen to 2 moles of electrons. Is that what you're asking? Yeah, you could have. Yeah, comes the same. Yeah. You can use basically any ratio of that. It's basically the same mathematically. Yeah. Other questions? All right. So if we wanted something like grams at this point, much like the previous problem, we could just use the molar mass, right, and figure out the grams of each of those things. But in this case, we do want volume, and these are gases. So, and we're given STP. So here we would maybe want to use PV equals nRT, and here we would be solving for solving for V, which is nRT divided by P. So if we do that for oxygen, the volume of oxygen would be nRT divided by P. And here we would put in our values. So for our N, we have 0.0875. We have our gas constant. And our temperature, which is 273, and our pressure, which is 1 atmosphere. And if we do that, 0.0875 times 0.08206 times the 273, that's about 1.96 liters of O2 would be made here. We can also do pretty much the same calculation if you like for our volume of H2. It would be our same guys, nRT over P. So put in our numbers, making sure to use obviously hydrogen's moles here. 0.08206 liters atmosphere Kelvin mole times our 273, again, all divided by 1 atmosphere. Going to get us here 0.175 times 0.08206 times the 273. 3.92 liters of H2 in this case. We also see here, if we look at what we saw earlier, I got, about twice as much hydrogen as I do oxygen here, right? Like we kind of saw in that picture in terms of the volume. First off, any questions on that calculation? You could have also, if you remembered Chem 50, not had to use the ideal gas law here because this was at STP, which means if you remember, I'm gonna do it here maybe. And only because it's at STP, there is a relationship, right, that 1 mole of any gas is equal to 22.414 liters at STP only. That means really you could have took the, say, moles of either one, really. Moles of, that's hydrogen, I think I took. And you could have just done a mole of hydrogen is 22.414 liters. And that would get you pretty much the same number there that you have on the bottom. And again, you could do that for oxygen as well. But we can only use that conversion, just a reminder, if it is STP conditions. If it's not STP conditions, you should not use that one. So you could always use the ideal gas law regardless of the conditions, just put the numbers in. But you can shortcut it if you wanted to, using that if it happens to be at STP conditions. Any questions on electrolysis cells? Variations on these problems is they will maybe sometimes give you how much you produce in a cell and ask something like, what was the amperage you ran it out or how long you ran the cell. Kind of doing the calculation backwards is sort of a variation on this type of problems. Any questions on any of that there? All right, that wraps up chapter 17, which should be, I think, the last chapter on our next exam. The third to last chapter, I think. This is about transition metals and also coordination compounds. A majority of this chapter will focus on complex ion and coordination compounds. But at the beginning, we're going to talk a little bit about transition metals, just to remind everybody about some of their properties. And that's good because, again, basically a lot of coordination compounds or complex ions involve transition metals in them. So let's talk a little bit about transition metals to begin this. And one aspect of sort of trends that we see just in general on the periodic table is something that's known as effective nuclear charge. And that is sometimes referred to as Z effective. And you might have remembered that from maybe Chem 50, you might have talked about it. And that's the positive charge that basically is felt by the electrons, right, from the nucleus. And the nucleus, which is positively charged because it has protons and neutrons. And protons are positively charged, neutrons have no charge. The electrons, which are negatively charged, are obviously attracted to the nucleus. And that's what kind of holds them there, right, so they don't go sort of flying off. That's also why, as we talk about certain things, especially with bonding, that there's only certain types of electrons that are involved in bonding, and those are those valence electrons, which are the furthest away from the nucleus. And that's because they're really not held as tightly. And part of that is because of the effective nuclear charge. So for example, if we looked at something like our friend lithium, which is 3, 1s2, 2s1, is this electron configuration. In terms of lithium, it has a +3 charge in the nucleus as it has 3 protons. And on the first energy level, there's a couple of electrons, but on the second energy level, there's another, and I'll just draw them like that, even though they don't circle or anything like that. But there's this idea of what is referred to as shielding that occurs with electrons in a higher energy level and those electrons in the lower energy level. So what that essentially means is, for example, if these were our 1s electrons here, they're pretty much going to feel that full brunt of that +3 charge because they're kind of like right there in the ballpark near them. And they're going to be held really, really tight. The problem, though, is when we get to, say, the electron that is really its valence electron here in lithium, which is this guy and this guy in my picture, it is now going to experience some shielding from those lower level electrons. And it's going to really kind of shield that electron from the full brunt of that positive charge. You know, it's kind of like when you go to a movie theater and you used to be able to sit down and pick your seat, but say you can still do that. And you pick your seat in the middle of the theater, right? And then right before the movie comes, somebody sits in front of you, giant hat on, right? And just shielded half of the screen and you can't see it anymore. And that's sort of the same idea that happens here. So we can actually calculate what is known as the Z effective, and that's actually the positive charge that electron is feeling. So if we were to do that, it would be really the positive charge of the nucleus, which in this case would be +3, minus the negative charge there, are added to the negative charge of our 2 electrons, which is -2. So that outer electron right here, which is its valence electron, is really only kind of feeling like a +1 sort of attraction to the nucleus rather than a +3 attraction. And as you might know, the strength of attractive forces increases with number, right? So like a +3 and a -3 is much more attracted to each other and held together stronger than if you had like a +1 and a -1. So because it only feels a +1 sort of attraction to that nucleus, it's not going to be held as tightly. And that is why when lithium loses an electron, this is the one that basically pops off. That is known as its valence electrons, right? And the lower electrons are sometimes referred to as core electrons, right? The guys that are closer to the nucleus and not held. In general, if we look at something like, say, sodium, magnesium, aluminum, and silicon, that's going from left to right on the periodic table. We do see that the effective nuclear charge increases. And that's because also as you go to the right on the periodic table, the numbers get bigger, right? Which means they have more protons as well to begin with, which means it has a much more positive charge. That also does what to our size, as we can see on the right there, it makes everything smaller, right? It brings everybody in. There's a much bigger positive charge in the nucleus, so the atomic radius starts to squeeze everybody in. That's why those electrons, even the outermost electrons, as you go to the right and really up on the periodic table, you are not as far away from the nucleus as, say, the guys to the left there. And that's what we see here. Again, because of that sort of increase in positive charge as you go this way, we do see atomic size start to decrease, right? And it gets larger as it goes this way. And that's also how the effective sort of runs as well. Now, our transition metals, which is the focus of most of what we're going to talk about in this chapter, is found here, right, in this area. And that's between group 2 and group 3 on the periodic table. These are our transition metals in there. The 2 rows on the bottom right are sometimes also referred to as intertransition metals, because if you follow their numbering, they should go right there on the periodic table. That's basically where they go. And they're sometimes referred to as intertransition metal. But for the most part, we will still deal with just these top transition metals. These guys are more nuclear sort of chemistry. Get those guys involved. Now, in terms of electrons, right, transition metals basically are our D block of electrons. Just a reminder, right, the first 2 columns here are the S electrons, right? These guys are the P electrons, those are the D, and our F block is down here. S orbital, you could hold 2 electrons, right? 1 and 2, right? P block, you could hold P subshell 6, 1, 2, 3, 4, 5, and 6. Obviously, D could do 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And 14, if you count it all the way from here to here, is where we can hold our F. And that is also how you can do electron configuration from the periodic table, right? It's equal to the period numbers, right? 1, 2, 3, 4, 5, 6, and 7. These are our N numbers, our principal quantum numbers, our energy levels is what those numbers refer to, right? By the way, though, a reminder that this, which is our first transition metal, is what d orbital? D orbital start on what energy level? They start on the third energy level. So that's actually 3D, one behind the period number. That's 4D, 5D, and 6D going that way. Yeah. So that's an important thing to remember. That's also why down here, this is actually 4F, right? That's where the F start. S's start on the first energy level, right? And P's don't start until the second, which is right here. That's 2P right there. Yeah. So this is basically 1S right there. So that's important to keep in mind. So when we do look at transition metals, they do show a very great similarity between periods and groups on the periodic table. When they do form ions, they can have more than one oxidation state can be found. That's also one of the ways that we think about transition metals and naming things that have transition metals, right? Those are the guys that can make a variety of positive charges, which is why when we name them, right, we typically use Roman numerals, right, to indicate the positive charge. The only exception, right, in terms of transition metals and sort of variable charges is zinc and cadmium, which makes a +2 charge no matter the situation, and silver, which makes a +1 charge. But everybody else there in the transition metal region can have a variable type of positive charge. And again, that's why we do use sort of those Roman numerals. And as we'll talk about naming in this chapter, we will use Roman numerals as well for those guys when we get there. Cations of complex ions are transition metals that are surrounded by a number of ligands, which are Lewis bases. So a majority of what we will see in this chapter when we start talking about complex ions is really a metal, and a lot of times that's going to be a transition metal in there, and they're attached to a number of things, say like water, which is a ligand is referred to. A ligand is a Lewis base, and you remember Lewis bases are things that do what? Lewis bases involve electrons, and they actually donate a pair of electrons. It is opposite of the Bronsted-Lowry definition of a base, which accepts an H+, but a Lewis base, which is pretty much all what complex ions are all about, will donate a pair of electrons, those ligands that are attached like water. In order to donate a pair of electrons, you gotta have some electrons to donate, and that's for water is that. And also helps to be polar, which is what water is a polar molecule. It helps in sort of donating it. Also things that have negative charges, right, are things that have extra electrons, so they're really good at sort of being Lewis bases. So things like chloride, Cl- is a good Lewis base because it's able to donate those things. And that's what we see here. This is our transition metal cobalt, again attached to, in this case, ammonia, which are all the ligands here. And ammonia is a good ligand because once again, it is polar. And again, it has those non-bonding electrons right there that it can donate really into our positive cobalt in this particular case. When we're done with this chapter, you will be able to properly name this guy right here. Be able to proudly say that's going to be hexamine cobalt 3 ion, and be good about that as well when you name that, rather than, you know, that thing over there, whatever that name might be. So we'll talk about obviously how to name those guys, but in this case, we do have our 6 ligands that are attached, and it does have a specific sort of geometry that we'll talk about, which also harkens back to geometry that we talked about when we talked about Lewis structures. Now, most compounds show some type of color because of the transition metal that's present, and also really a lot of times has to do with the ligands that it's maybe attached to as well. And it is able to absorb visible light of a specific wavelength. And when we look at a solution that has a particular color, we are actually seeing the light of that color being absorbed, or it's going to absorb the complementary color to that. Complementary color, yeah. So when we see a color of a solution, it's actually the complementary color to basically the color of light that's being absorbed. So that's why when you set your spectrophotometer, You don't set it, for example, when we had those red solutions, when we did like the equilibrium constant experiment, we didn't really set it to red's wavelength, but we set it to a different wavelength, maybe greenish or blue, depending on where you were in terms of that. So we do see the color as being complementary to the one being absorbed. And a lot of compounds are paramagnetic, and paramagnetic means, anyone? You have unpaired electrons. That's basically what that means. So if you have paramagnetic, means you have unpaired electrons. I don't know. Maybe they teach these things again. I don't know. Dimagnetic means that you have paired up electrons. Yeah. So when electrons are paired, right, they have spins. Spin quantum number. Yes. Electrons, arrows, plus a half, right? Minus a half. I'll have to take a field trip to Chem 50 and see what they teach there these days, apparently. All right, but this is a quantum number, yes? There's 4 of them. Yes. N, L, M sub L, M sub S. They teach these things anymore? No, they do? Okay. But this is a spin quantum number, and that's why electrons cannot go into the same orbital in the same direction, right? Pauli's exclusion rule. No 2 electrons could have the same 4 quantum numbers. All right, well, that's something to think about for the rest of the day. I think we will stop there.